Welcome to Mathematical Colors and Codes, Episode 3. I'm Sandy Eklund, the mathematician, and I'm also a librarian at City of Fairfax Regional Library. Now, the last two episodes, we talked about prime factorization and how you can show it using colors. Then we talked about how you can use the colors to make coded messages. Today, I'm going to talk about non-decimal bases, or as I like to call it, alien math. Now, you'll notice again I'm wearing my original prime factorization sweater, and part of the reason for that is my family and I noticed when I was making the sweater that a cool thing about it is it would even work on alien planets. What do I mean by that? Well, if you think about it, our number system, we have certain numbers, 1, 2, 3, 4, but I'm sure they developed counting on alien planets, but surely they wouldn't use the same numbers to represent the amounts. Well, as long as the aliens aren't colorblind, they can still use the sweater because it shows the numbers with colors. In fact, we had this joke that we said if an alien ever knocked at the door, we would say, "Quick kids, get the sweater," and we would bring it to prove that we had intelligent life. Okay, but that's not the only reason that the sweater is good for aliens. The other reason is because I've got rows of 8 on the back, rows of 3 and 2 on the sleeves, and of course the rows of 10 on the front. Now, why is that significant? Well, on human planets, on Earth, we all have 10 fingers. So we all count using base 10, or which is known as the decimal system. That's from the Latin word for 10. And we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, suppose you're on an alien planet where everybody has 8 fingers. You're going to develop a counting system, but it's probably going to end up going something like this. 1, 2, 3, 4, 5, 6, 7, 10. 11, 12, 13, 14, 15, 16, 17, 20. 21, 22, 23, 24, 25, 26, 27, 30. 31, 32, 33, 34, 35, 36, 37, 40. 41, 42, 43, 44, 45, 46, 47, 50. 51, 52, 53, 54, 55, 56, 57, 60. 61, 62, 63, 64, 65, 66, 67, 70. 71, 72, 73, 74, 75, 76, 77, 100. And then you go 101. Oh, by the way, don't let any little brothers and sisters who are learning how to count hear this video because it's going to really confuse them. But that way of counting, where you just have the digits 0 to 7 instead of 0 to 9, that's called base 8 or octal. And that has to do with the rows of 8 on the back. Now, suppose you only had 6 fingers. What would counting be like on that planet? Well, it would go something like 1, 2, 3, 4, 5, 10. 11, 12, 13, 14, 15, 20. 21, 22, 23, 24, 25, 30. 31, 32, 33, 34, 35, 40. 41, 42, 43, 44, 45, 50. 51, 52, 53, 54, 55, 100. You get the idea? Okay, let's try it with, suppose you are on a planet where they have 5 fingers, but they each only have 1 hand. You would probably count like this. 1, 2, 3, 4, 10, 11, 12, 13, 14, 20, 21, 22, 23, 24, 30, 31, 32, 33, 34, 40, 41, 42, 43, 44, 100. So you can see how these other bases work. That was base 5, by the way. So whatever base it is, you have that many digits, And when you run out of digits, then you go on to another, well, we call them decimal places, but it would be octal places or base 6 places. Now, those ones that I've done, base 8, base 6, base 5, we're going to use next time to make coded messages. But I do want to show you one more that's not so useful for coded messages, but they actually use it in computer science. And so I want you to know how it works, and that's base 16. It's also called hexadecimal. Now, with all of these, the base is how many digits you have. So base 10 has digits 0 through 9, that's 10 digits. Well, what are you going to do for base 16? It's going to have 16 digits. So what we do is when we run out of 0 through 9, we start using letters of the alphabet. So suppose I'm an alien with 4 fingers on each hand, but I've got 4 arms and 4 hands. Now how will we count in base 16? It would go something like, and if I was good at animating, I'd animate that, but you're just going to have to pretend that I've got 4 hands. So it would go something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, A teen, B teen, C teen, D teen, E teen, F teen, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 20A, 20B, 20C, 20D, 20E, 20F, 30. 31, 32, 33, 34, 35, 36, 37, 38, 39, 30A, 30B, 30C, 30D, 30E, 30F, 40. And you get the idea. These ones take a lot longer to get very high, so I'm not going to keep going. By the way, if you would figure out how old your parents and grandparents are in hexadecimal, you'll make them happy, because the age sounds much smaller when you use it in hexadecimal. In fact, if you know anybody who's turning 60, you can tell them, oh, that's nothing. You're only in your 30s in hexadecimal, and next year you're going to be 3D. So anyway, those are different bases, and the nice thing about the sweater is you can actually use the prime factorization charts to translate between bases. Suppose I'm an intergalactic merchant and I sell things on different planets. Well, I have to change money and I have to change number systems when I go to different planets. So one way you can do that is just use the chart. And let me show you what I mean by that. Okay, here's the back of the sweater where I've got rows of 8. I use the same colors as on the front, so the amounts are the same. What they represent is the same, but they're in rows of 8, so the patterns are all different. So now you could count, but it would work well for counting an octal, because it'll be 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 24, 25, 26, 27, 30, and so on. So this is going 10, 20, 30, 40, 50, 60, 70, 100, and so on. But the thing is if you wanted to translate back to decimal and figure out what they represent, you could use the sweater. So this square with 3 blue and 1 red, we said that was 30 in octal. Well, we could turn the sweater over and figure out where do we have 3 blue pieces and 1 red, and it turns out to be 24. So you can use the prime factorization chart as a way to translate between number systems. This week, the coloring pages that you can download give you prime factorization charts in several non-decimal bases. Now, this is similar to the chart we did in decimal in episode 1.
So if you haven't done that prime factorization chart from episode 1, this will be a good time to go back and do that first before trying to do these, because it's a little more complicated to use non-decimal basis since what we're used to is counting in decimal. Okay, I've put 2 examples here. We're going to start with an octal chart, that's base 8. But you're going to fill it out exactly the same way we did the decimal prime factorization chart. Just fill in, give a color to each prime number, and then fill in all the multiples. Now, it's going to work out more nicely for you if you use the same colors you did for the decimal prime factorization chart. Then you'll be able to use the decimal chart to help you fill out these other ones, and you can see the relationship between the numbers and the patterns if you use the same colors. So filling this out the same way I did the 10 chart, I'm going to make 2 the color red, and then I just count 1, 2, 1, 2, 1, 2, 1, 2 to fill in all the multiples of 2. So in base 8, they line up nicely. So it's just 2, 4, 6, 10, 12, 14, 16, 20. And that's because 2 plus 2 plus 2 plus 2 is 8. So it goes evenly. Then the number 3 gets a blue color. And then I count 1, 2, 3, 1, 2, 3, 1, 2, 3, and fill in blue. Okay, and you can see it makes a pattern, though this doesn't line up because 3 doesn't go evenly into 8. Okay, the next number 4 has one section not filled in, and that always means it's a power. So you give it one more red section. And then the 4 does go evenly into 8. So look at the nice pattern this makes. It's kind of like 5 in the decimal system, because if you look at it, the ones that we got when we counted 1, 2, 3, 4, you get 4, 10, 14, 20, 24, 30, 34, 40, 44, 50. Okay, then the next number 5 gets a green color, and then you count 1, 2, 3, 4, 5. That gets you to 12, then to 17, then to 24, then to 31, and so on. And it's kind of confusing in base 8 because this isn't how 5 adds up in decimal that we're used to. But you can always look back at the prime factorization chart in decimal and make sure your colors are showing up in the same order as they did in that chart. And that way you can be sure you're doing it right. Okay, then 6 is already filled in. 7 gets a new. So we've got 7 is yellow, and then just count 7. And you get 16, 25, 34, and 43. And notice that makes a diagonal. That's because it's 1 less than 8, which is the base. Okay, when you get to 10, there's one section not filled in, so you know it's a power, so you give it another section of red. And when you're counting to 8, that's going to put you at the end of the row every time. So 20, 30, 40, and 50 all get another section of red. Okay, then we get to 11, and this is the one that feels strange, but 11 in base 8 is 9 in decimal, and you see it's got a section not filled in, so that means it's a power. So you fill in another section of blue. And then once you get to the next row, the easiest way to add 11 or to add 9 is just go up 1 row and to the right 1. So, and you can do it either way, either count 9 or just go up 1 row. That's the same as adding 8, and then over 1 for that 1 more. So that gives us 11, 22, 33, and 44. Kind of interesting that it's the same as if you would add 11 in base 10, but the 11 is a different amount. Okay, then the next number was 13, got purple. 13 in octal is actually 11 in decimal. But again, you can just go up a row and then over 3. So that brings you to 26. Then up a row and over 3 brings you to 41. And of course, when you get to the end of the row, when you're counting, just go up to the next row. Okay, and 14 was already filled in. 15 got a new color, and you'll go up a row and then count 5. Brings you to 32, then up a row and over 5 gets you to 47. And that's how you'll continue to fill out the chart. When you get to 21, then you're going to go up 2 rows and to the right one. So you can use that same idea with every row you go up. Okay, let's also look at base 7. Base 7 gets a little bit confusing because 7 is prime itself. So in decimal, we had the 5s and the 2s and the 10s lined up. In base 8, we had the 2s, the 4s, and the 8s lined up. Well, in base 7, nothing's going to line up except for 7 itself. So let me show you how that works. First, if you fill in the 2s, you go 2, 4, 6, then 11, 13, 15, and 20. It's very strange because when you add 2, you don't always get an even number if your base is odd. So the way to do it is just count 1, 2, 1, 2, 1, 2, and you should end up with a pattern. Though in base 7, they don't line up vertically like they do in the even bases. Then do 3. 1, 2, 3. 1, 2, 3, you get 6. 1, 2, 3, you get 12. 1, 2, 3, you get 15, and so on. Then 4, you know it's a power because there's a color not filled in. And then you'll count every 4 to get another red section. Then 5, count every 5, you get 13, 21, 26, 34. It's very strange, but you can see it does follow a pattern. Okay, 6 is filled in, then 10, this is base 7, so that's like decimal 7, and that will just fill in right up the chart. So 10 plus 10 is still 20 in base 7. Or you could count 7 over, but that always gets you to the end of the row. Then 11, you can see it's a power. It's got something that still needs to be filled in. And then to find the rest, just go up 1 and over 1. So it was 11, 22, 33, and 44. Then 12 is a power. So you'll fill in one more section of blue and then go up 1 and over 2. So you get 24, and 36. Then 13 is already filled in. 14 will get a new color. And to find the other multiples, you'll go up 1 and over 4. So that got us to 31 and then 45. And so on. So that's how this works in base 7. So I hope that was enough to get you going, to get the feel for these. This week's coloring pages, I've got 5 different charts. I've got base 8, which is octal, base 7, base 6, base 5, and just for fun, base 16. I think you'll get the most out of this if you use the same colors for all the charts and use the same color as you did for the decimal chart. And then you'll be able to see how the patterns change. And it's also fun to notice which ones are the most similar. I'll just let you think about that. But I hope you'll have a little bit of fun with this and just see how are the different charts alike and how are they different.
Thank you for watching Mathematical Colors and Codes, Episode 3. Tune in next time when we'll take these ideas about non-decimal bases and use them to make coded messages.